Hello everybody. In today's video we're going to be discussing acceleration. Now to start off with, we all know we have two pedals in a car, and we can think back to the name of what this one is. Now most people call this the gas pedal, but it can also be referred to as the accelerator. And what does it do when you put the pedal to the metal there? Well, it changes your speed. It makes you go faster. And that's what acceleration is. Acceleration is a change in speed. In the American system of units, we use miles per hour per second. So it's how much your speed is changing, miles per hour, for any given second in time. A very classic way we use to describe the acceleration of the cars is what we refer to as the 0 to 60 time. And basically what that is the time it takes to go from 0 miles per hour to 60 miles per hour. Now this is basically an acceleration. We're looking at the time it takes to speed up, which is a change in speed in acceleration. So if we have an example car that goes from 0 to 60 miles per hour in 5 seconds, what is its acceleration? Well, it would be basically 60 divided by 5, which is 12 miles per hour per second. In physics, however, of course, we do not use miles per hour. Instead, we use meters per second. In the case of acceleration. So you can see at the bottom here, I wrote it in two ways. In the meters per second, kind of the traditional way where it's written out, where you can really see what each individual second is. The first second having to do with the speed, the second one kind of defining the acceleration. However, we often simplify it to meters per second squared. And you're going to see me kind of use either way, but when I write it down, I generally write it down as meters per second squared. It's definitely simplified that way, but I think you lose a little bit of the meaning of what each of those seconds are kind of individually illustrating. Let's look at an example problem. A 747 needs to be moving at 80 meters per second to take off. So if it starts from rest and it reaches a speed, that speed in 35 seconds, basically on the runway, what is its acceleration? Well, what we're basically going to do is we're going to take that 0 to 60 question that we had before, and we're just going to adjust it for some different numbers. And in this case, we're going from 0 meters per second to 80 meters per second. Now, where the 0 meters per second came from was this statement here, which is going to be a very common statement we're going to see quite often: from rest. From rest means that the starting speed is 0. So if ever you see from rest, it means starting speed of 0, and you're going to see that quite often. Now, what I'm going to do here, I'm going to do the same math I did for the 0 to 60 question. And what I did there is I took that 60 and subtracted from 0. In this case, I'm taking the 80 meters per second, subtracting it from 0 meters per second, and dividing it by the time to get my overall answer of 2.3 meters per second squared. Therefore, the relationship, the trick that I've been using, is the acceleration of an object is defined by its change in speed over time. So this delta here, we've seen it many times before. I've seen it a lot in chemistry. Delta means change in something. So, and v is speed. So our change in speed or change in velocity divided by time is defined as our acceleration. Now it should be, I'll get onto that later. Let's do another example of this. This time, not doing a 0 to whatever type of question. So we have a car that's moving 5 meters per second and accelerates at 3 meters per second squared for 7 seconds. How fast is it moving after this period of acceleration? Well, I'm going to take that same formula that I just showed, break it up into what delta means. Delta means final minus initial. So F is the final speed, the speed that ends with. This is what we're trying to solve for. While I stands for initial, which is the starting speed. In any one of these questions, in any one of these physics questions, what I highly recommend is writing a list of the variables and their units off to the side. Take the word problem and figure out each of the important parts. Now, I call this list kind of a funny name. I call this the shopping list. So the shopping list includes our acceleration, which is 3 meters per second squared. Our final velocity, which is what we're looking for. As I like to put it down with a question mark to remind me that's what I'm looking for. My initial velocity of 5 meters per second, and my time of 7 seconds. So what I do is I take all these values and I plug them into the equation with the units. Now it's important that I include the units. It's a good idea in general just to check over your answers, make sure that everything makes sense when you get the unit that makes sense in the end. That means you probably did the math right, but it's also a requirement for any Regents exam. Any question that we have that you have to show work, you have to make sure that you include the units in there. Definitely don't want to lose points off of that. All I did was just simplify this a little bit, multiply both sides by 7. I get 21 meters per second is equal to the final velocity minus 5 meters per second, and I end up with a final velocity of 26 meters per second, which is pretty fast. It's about highway speed. Now, a quick thing that most people have heard of the term acceleration before, and most of the time people use it correctly. However, I often hear, including I heard this at the beginning of this year a lot, was people using acceleration for speed interchangeably. And I remember when I learned the difference between acceleration and speed, I was pretty young and I was playing a racing video game. And I remember the two statistics being top speed and acceleration, the only two that I cared about because, playing a racing game. And I remember my brother needing to explain the difference between the two because I never figured it out on my own. So just remember that speed and acceleration are two separate things. Now, they are very similar to each other, where we have a speed is a change in distance over time, while the acceleration is a change in speed over time. So they have that kind of same idea where they're changing something over time, but you have to pay attention to what is changing. Now we're going to jump into looking at our graphs. So we're used to seeing constant velocity in our different graphs, our distance versus time graphs, and our velocity versus time graphs. Now we're going to be looking at what acceleration looks like for these type of graphs. And quickly you can see the difference between distance versus time graph and what you're used to seeing, and that is the fact that we have a curved line. The curved line is indicating that we have a change in speed, that we have an acceleration. So whenever you see a curved line, that means acceleration is happening. And in order to find that acceleration, in order to properly discuss this acceleration, we have to see how the slope changes. A positive acceleration, one where you're speeding up, is where the slope gets more and more positive over time. So if we look over this right one, what I've done is I've drawn a tangent line. And I drew a tangent line right at 0. You can see that the slope of this tangent line, which is the slope of this graph right at the 0 point, is right around 0. If I draw it then at the very end, so I'm drawing it about right here, the tangent line, we can see that is much more positive. So we started from 0, we've gone more positive, which means this refers to as a positive acceleration, or an acceleration where we're speeding up in the positive direction. Well, a negative acceleration is where things get less and less slopey over time. So we start off with a very high slope, and we end up with a very low slope. Or it could also mean getting more negative, is also a case, in which case is getting more and more of a negative slope. So for this one, if we look at this left graph, we can see that it starts off at a high slope. I drew a tangent line. And then at the end, you can see the slope is pretty low over here. So we started off at a high speed, because again, slope is speed, at high speed, and we ended at a low speed. And this would be an example of negative acceleration. Now, off of a distance versus time graph, there's no way for us to find the exact acceleration, except for some calculus things, but don't kind of expect us to do this. And this is actually where velocity versus time graphs come into play. Now, velocity versus time graphs they're not as intuitive as distance versus time graphs. It's harder for us to instinctually look at them and go, this is what the object's doing. But where velocity versus time graphs really shine is when acceleration is in play. Now you can quickly see that this velocity versus time graph is very different from the ones we're used to. We're used to seeing velocity versus time graphs only having flat sections, but now we're seeing sections that have a slope to them. And that slope is the acceleration. So if we find the slope at any given point, that is the value of the acceleration. Just like for a distance versus time graph, when we find the slope, it gives us a speed. For a velocity versus time graph, when we find the slope, it gives us acceleration. So a negative slope would be negative acceleration. This is often slowing down, though it could be speeding up in the negative direction. So for example, this over here would be slowing down. You can see the speed starts off high and it's getting lower and lower and lower. This would be a negative acceleration over here. A flat is a constant speed. Now, don't confuse this for a flat section of a distance versus time graph. We're still moving. We're moving at a constant velocity, however. And of course, a positive slope would be a positive acceleration. We've learned this before for velocity versus time graphs, but it's important to know that the area under the curve is the distance. So the area of this section is distance. Now, for these types of graphs, what you'll often have to do is break it up into sections of triangles and rectangles and add them together to find the overall distance. So for a velocity versus time graph, though it's not as intuitive as a distance versus time graph, you can get much more information out of it. You can get the distance, you can also get the acceleration. And getting the acceleration is something that you can't do off of a distance versus time graph, at least very easily. Another thing to note is that in this class, we will never see a curvy line as a correct answer for a velocity versus time graph. Now, is it possible to have a curvy line in a velocity versus time graph? Absolutely. In the real world, you can definitely have speeds that are changing and changing how they're changing, basically an acceleration that's changing. However, in this class, we focus on constant accelerations. So we won't see any type of curved line unless it's the wrong answer of a multiple choice question. You won't be seeing a curved line. Acceleration versus time graphs. So this is obviously a new type of graph that we're looking at here. Acceleration versus time graphs will always be flat, just like we're kind of used to before with the velocity versus time graphs. But now they'll always be flat. We'll never see a curved line or a line with a slope. Now, the acceleration, you just read off of the graph to see what the acceleration is. And then, of course, if the acceleration is at 0, well, that means it has a value that is 0. Now, I wanted to bring us back to this, this picture over here. We described this as the accelerator over here because it's when you push the pedal to the metal, it speeds you up. But I also want to point at this pedal, which we often refer to as the brake. The brake is also an accelerator. If you press the pedal to the metal, in this case, you're going to change your speed. In this case, your speed is going to be slowing down. And this is what I've been talking about, where negative acceleration is slowing down in the positive direction, or it could be speeding up in reverse. But in this case, what this pedal does is it slows you down. It's still changing your speed, and a change in speed is an acceleration. Now, in this class, we won't be using the term deceleration often. Now, we can still use it when we're talking to one another is okay, but for the actual term in physics, deceleration is not a term that we use. Instead, we like to assign a direction to the acceleration because acceleration is a vector. So a positive acceleration is generally when we're speeding up in the positive direction. And a negative acceleration is either when we're slowing down in the positive direction or we're speeding up in the negative direction. So both of these pedals can properly be described as an accelerator, and that would be perfectly fine. All right, I hope you have a good one.